All right, this will be the Analytics 1 lecture on sampling distributions. Our learning objectives and new content for today are going to be being able to talk about what sampling error is and how samples of data really help us understand what's happening in a full population. The big motivation is going to be that most of the time we don't actually have all of the data we need to answer some kind of question. And so we're going to be really spending a lot of time today thinking about how we can get good enough information from a sample and figure out how reliable it actually is. And the way we're going to do that is with something called the central limit theorem. And so we're going to learn how to apply the central limit theorem to some probability questions. Our vocabulary will be sample, population, estimator, estimate, sampling error, sampling distribution, and the central limit theorem. Oh, also standard error, which is a part of the central limit theorem, which we'll talk about briefly. All right, we're going to do a discussion of what sampling, estimators, and estimates are. I'll show you a cool visualization, again, I put together with a little simulation on how this stuff works. We'll talk about what the central limit theorem is and some probability applications. The title of this slide is "Nothing is Knowable with Certainty, but Data and Models Can Help." And that's the truth. When we come down to think about what we actually know for certain in the world, there's very, very little we know. And we always think about things in the context of models. That as we kind of imagine how a situation actually takes place and then use observations with data we see around us to sort of change our perspective of the world. We're going to call that way we think about the world a model here. But since we don't always know all of the data, we're going to have to figure out how to operate with limited data and without all of the information we can have. So our course from here out is going to focus on two things. The first is going to be on how we can improve our model of the world. That is the methods by which we can adapt the way we think about data. And the thing we're going to be focusing on today is how our understanding of the world could be limited by the fact that we will never have all of the data we need to perfectly understand things. So recognizing that there's limitations about what we can observe and determining how that impacts what we see and what we think about. So if we were to think about some of the biggest issues we would be interested in personally maybe, or from a policy perspective, even with COVID, we might wonder things like what are the long-run health implications, what's the expected total mortality, how do various policy interventions impact its spread, what are the economic trade-offs to be made with those policy interventions. But the truth is, these are questions we've never experienced anything like this when we had data even near as good to try and figure this kind of thing out. And so we are, as a society, as a planet, still trying to figure out how to make assessments with limited information here. So to make clear the kind of statistical terms we're going to talk about briefly, I'm going to give you an example with elephants, which is going to seem a little bit silly, but it's actually kind of slick. So this is the truth about elephant. This guy is the truth. And this is what we see when we look at data. Now, there is an old parable about 6 blind men approaching an elephant, and each one is convinced of their correct interpretation about what they are approaching based on their limited view of the world. Okay, so each one of these guys is taking a sample. They have some claim about what they actually observe in the world. But what we're going to talk about today is the conditions under which we can actually get closer to the truth, even just from samples of information here. So what we're going to talk about is how to approximate reality. And what we're going to do is generate something called an estimator. And an estimator is simply some object we calculate from a sample of data whose whole purpose is to approximate some true feature of the population that we are interested in. A sample average, x, is what we call an estimator for the true population mean, mu. And the sample standard deviation is an estimator for the true population standard deviation, sigma. Now, unfortunately, estimators aren't always perfect at portraying the features of the population we intend them to. And so there's two real kinds of limitations in how effective estimators are, and we have specific terms for the kind of limitation they have. The first is called consistency, and consistency is a feature of an estimator that says as your estimates your estimate that you get from a sample of data gets better and better the more data you have. Okay, we would say an estimator is consistent if, as we get more and more and more and more and more data, our perspective on the truth becomes clearer and clearer. The other term is called unbiasedness. We would say an estimator is unbiased if, on average, our perspective on reality is correct, independent of how much data we have. So the latter is not a statement about how many pieces of information we have to calculate something. It's that on average, if we do a particular procedure with our data, on average, we're going to be correct. All right, so let me give you an example in terms of our elephants, what unbiasedness is. So our blind scientists have decided to create an estimator here to study an unknown animal. And their estimator, what they're going to do to interpret their data is they're going to approach this animal 10 times from random starting points and list the features of this and hopefully come to a conclusion about what those features all make up. Okay, we'd say their estimator is unbiased if on average they come to the right conclusion. So each scientist is going to go approach this unknown animal, touch it 10 different times, come back and state what they've seen. So we would say this approach or this estimator is unbiased if the average scientist yells elephant. This doesn't mean that they have to get it right every time. Sometimes, by sheer chance, you may have a scientist who happens to touch the trunk 10 times and conclude that they've ran into a python rather than an elephant, but on average, they get it right. So some places that bias typically come from are either that the sample isn't representative of the full population of data, or there's something inherently weird about, not weird, but the way you are calculating your estimator leads you to misstate something about the true population value. So here's an example where we're looking at our true elephant and we want to say, if we applied our estimator to this sample of data, is there a bias? That is, would our scientists be able to come up with the answer most of the time? And the answer is yes. In theory, in this sample, there's no bias here because if you're brave enough, you could approach the entire elephant, which means in my 10 samples, when I approached the elephant, I could independently touch the tail, the trunk, the tusks, the ears, the feet, and eventually figure out what it is. On this example, though, this is a sample that would create a bias because the sample itself, the sample of data, is not representative of the full elephant. So since there's a fence here, no matter how many times our scientists would approach this, if they approached it 10 times, they're likely to run into the trunk every time. And then you send another scientist out and they try it again and they run into the trunk every time, et cetera. So what happens is every one of these scientists is going to come away with the perspective that this is a snake, which means on average, they're not getting this right. This is what we would call a biased sample. So some examples of samples that or estimators that could be biased here. We would say that the mortality rate for COVID based on early data from New York City is probably a biased estimate of COVID-19 mortality rates elsewhere. And the reason is New York City has very high population density and an above average number of nursing homes, and older populations have a higher mortality rate, which means the sample of data is not representative of the full US population. This is likely to lead us to concluding, if we were to use this as an estimator for the full mortality risk for COVID-19, we would probably overstate the mortality risk in places that had a more uniformly spread demographic mix. Consistency is another way we can describe these things. We would say, this is another way of describing the limitations of an estimator. And so our estimator here is we're going to approach the animal n many times from random starting points and list the features. And we'd say that an estimator is consistent if, as n gets arbitrarily large, we end up with an arbitrarily close description of the true population value. So if, as we let scientists touch this animal with independent starting points more and more and more times, they become more and more likely to yell elephant. We would say this is a consistent estimator. So again, here in this setting, our estimator would be consistent because as every time they get more information, they touch more and more of the elephant is always available, this means they get more independent data points. Our sample on the right, where also our estimator here would also be inconsistent, because even as we let our scientists touch this elephant more and more and more times, they're still only going to be approaching it from the front because of the fence, which means they're only going to touch the trunk, which means no matter how many times we let the blind scientists approach this elephant, they're not going to get information that's going to lead them to the correct conclusion. So what I want to do now that we've got an idea for how these things actually operate conceptually is describe for you how these would work in the context of an actual statistical application here. So we are very familiar by now with a binomial random variable. So we're going to start with a binomial random variable x that has 10 trials and a 40% chance of success. We could in fact calculate the true population values we might be interested in here, the mean mu, which is the number of trials we have, 10 times the probability of success, 0.4. And we would find out that on average, the mean should be 4 in this distribution, the true population mean. And similarly, the standard deviation here is 1.55. Now, as I mentioned, what we're going to be focusing on here when we think about how to learn some information about populations, the two most common things that data analysts study are typically the mean and the standard deviation of population, because they give us an idea of what happens on average and how much our data are spread out around that. So I'm going to focus here only on the mean, but you could, of course, think about the standard deviation in a similar way going forward. So what we're going to do is propose an estimator here for a population mean that will turn out to be both unbiased and consistent, meaning it's going to be a very well-behaved estimator and give us a true, accurate portrayal of the true population. All right, so my proposed estimator for the population average mu is the sample mean x bar, and a sample mean is just an arithmetic mean where we're going to take all of our numbers and divide by the number of observations for a sample of data. So what I've done here is I pulled a random sample of data from that population, that binomial population. I plot the distribution of that data, and then I've calculated the mean here. And that mean is 3.48 in this setting. How close is that to the true population mean? Well, it's not exactly right. So the true population here is on the left, the true mean is 4, and our sample mean is 3.48. Okay, we have undersampled data on the far right tail and oversampled data to the left of 3, which means our sample average has what is called sampling error, which is the difference between the sample and the true population value. And so what we're going to do here is we're going to plot the sample average here from our first sample from the population. And then we're going to go ahead and take another sample because we're going to first explore whether there is any bias in this sample. And to get an idea of bias, we need to know if on average, in expectation, the sample average reflects the true population mean. And so to do this, we're going to take a bunch of samples from this distribution and compare them to the population mean. So here's our first sample. We're going to plot that same information I just talked about where the sample average was 3.48. We'll take another sample. We can see the distribution here in blue is the sample distribution against the population distribution. We're going to plot that new sample average 3.92. Again, we can draw another sample 3, sample 4, sample 5, sample 6. And so all we're going to do here is plot out these sample distributions and see how they actually stack up on average. Now, because this is a little bit slower, I'm going to speed this up again so that we can watch the evolution of all of these samples that we take from our population here. So we're going to take 1,500 samples out of this population. Each one of these samples is, again, randomly drawn from this true population here on the left in gray. Those blue bars popping up and down on the left are showing you what each sample's data points actually happen to look like. And we're going to plot the mean of those on the far right-hand side, each one of those dots every single time. All right, now that it's completed, we can see that in this set of 1,500 samples, the average of all of these sample averages here is actually 4.01. Now, as compared to the true population mean of 4, this is arbitrarily close. And again, if we were to make this not even 1,500 samples, but 3,000 or 15,000 samples, this sample average would be exactly the true population mean, which is a way of saying that a sample average is an unbiased estimator of the true population mean. So just simply taking a sample average will do a good job of portraying the true average of a set of data for us. Now, there are two things to note about this set of sample averages here. On the far right, we're going to call this thing a sampling distribution, and it reflects all of the possible sample averages we could calculate from this set of data. And the first thing to note is that it is normally distributed, and the set of sample averages are more condensed than the underlying data. That is, they fall between the values of 3 and 5 for the most part, and we can see that that is just a subset of all the underlying data that could have been pulled here. Now, this will turn out to always be true and is a demonstration of what we're going to call the central limit theorem. Now, what is the central limit theorem? The central limit theorem is a way of understanding how sample averages behave from larger populations of data. And here's what it says. If we were to consider any random variable x, we don't care what the underlying data look like. We don't care if they're normal or binomial. It doesn't really matter what they are. That has some mean and standard deviation. And then we go and take a sample of size n from the population and calculate a sample average. Those sample averages are going to be normally distributed around the true mean mu with a standard deviation of that set of sample averages given by the population standard deviation divided by the square root of n. This object is called standard error, and it's a way of describing how spread out your sample averages are. In English, what this says is the more data we use n to calculate our sample average x, the closer that x bar is going to be to the true mean. That is, the more data we use, the less likely it is to differ from mu by a lot. And the more spread out the underlying data is, the more data we need to guarantee that our sample average is actually very close to our true population mean. Now, here's an example of how this works. Suppose we know that we had a salesperson who's going to sell on average 4 sales a day. This is our binomial example. The expectation of that binomial random variable is 4, and the standard deviation was 1.55. Suppose we watched our salesperson for 10 days. That is, we take a sample of 10 days out of the year. We could ask what the probability is that she averages less than 3.5 sales per day. That is, what is the probability that a sample of 10 days is going to have a sample average of less than 3.5? So we're going to do the same things we always do. We'll define the random variable x bar to be the average number of sales in 10 days. Our event here is x bar less than or equal to 3. What type of random variable is this? Well, the central limit theorem tells me that all sample averages follow a normal distribution around the true population mean 4, and the standard deviation is given by the standard error, or the population standard deviation 1.55 divided by the square root of your sample size, how many days you use to calculate your sample average, which here is 10. Since we know this is a normal distribution, all of the things we've done with continuous random variables and normal distributions before apply here the exact same way. So we're just going to calculate p of some normal random variable is less than 3.5. So this is just norm.dist of 3.5, comma mean, comma standard deviation, comma true, which works out to being 15.4%. The next property of a sample average we need to discuss is consistency. And that says that the more data we use, the more likely we are to get a sample average closer to the population mean. So what I'm going to plot for you is the sampling distribution that comes from taking larger and larger and larger sample sizes. So what we can see here is we, in our previous simulation, started with a sample average that used 25 data points. Here, we're starting with 5 data points on the left. We can see that that sample average distribution is more spread out. But as we get closer to using 100 data points from the population, this distribution gets tighter and tighter and tighter around the true mean 4. So when we only use 5 data points, they were both centered around 4, meaning they're both unbiased. On average, we get it right. But as the sample size gets larger and larger and larger, we end up getting closer and closer and closer to that true mean. So instead of having a range of values here from like 2 to 6.5, When we use 100 data points, they range from 3.5 to 4.5. The standard error of our estimate of the true mean gets smaller and smaller and smaller the more data points we use. That means that X bar here is a consistent estimator as well of the population mean. We can see visually what this means for probability calculations, what the probability of our sample average being less than 3.5 is. Well, it depends how many days you use. If you only use 10 days, we already determined that we would see a 15.4% chance that our salesperson might have an average of 3.5 sales or less in a 10-day period. But that drops to 1.1% in a 50-day period and 0.06% in a 100-day period. So we get an idea here that it becomes less and less likely to see these data points that are very far from the true mean the more data we use in calculating our sample averages. And that actually happens very quickly as n gets bigger. All right, so in summary, we can learn about populations from samples. It's very doable, but we need to be cautious about whether the way we do it will give us an unbiased and consistent estimate about the true population characteristic we're interested in. If we use a sample mean, it turns out that's a good way of describing the true population mean. We also know, however, that since our sample mean is a continuous random variable, the probability that we ever get the sample mean to be the true population mean is always going to be 0. We'll never know the true mean exactly. But the central limit theorem will help us understand how likely it is that our sample average is very far away from the true mean. And this turns out to depend on only 3 things: our sample mean that we happen to calculate, the true population mean, and the standard error of that estimate.